Need to know that what are cross-cutting concerns, for example, CCC. So these are system-wide responsibilities like security, speed, and reliability that cannot be isolated because they affect and span across every single layer that we talked about. And for example, the problem tangle code bloat. In a clean layered architecture, you want every layer to focus entirely on its own job. High cohesion, for example, business logic should only calculate business logic, should not be doing all everything. So presentation core responsibility is to render user dashboard. That's the presentation layer. Security layer validates the session token. Business layer calculates interest rate. Data layer fetches from the database. And standard examples of cross-cutting concerns is that software architect classifies system needs into core features and horizontal cut-throughs. For example, cross-cutting concerns what the layer does, processing a payment, adding an item to the cart, creating a user profile, whatever. But a cross-cutting concerns system utilities, for example, security and authorization, ensuring a user has the right permission before touching any data or screen, logging and diagnostics, recording system behavior errors and background activity to text files for debugging, for example, performance caching, storing frequent database results in memory temporary locations to speed up response time across applications, and exception handling, catching unexpected code crashes so the user sees clean error message instead of raw server code. And how the architecture solves this problem is aspect-oriented programming. This is just a way, instead of writing code directly inside the layers, you extract the cross-cutting concern into a standalone module called aspect. You tell the system framework automatically inject this logging aspect right before any method executes in any layer. This keeps the individual layer completely clean, simple, and focused strictly on their primary job. Now, we need to describe the three layers architecture. We know that it divides a system into three clean layers: a presentation layer, application layer, the business logic, and the storage layer, the database. Now, the top tier is presentation layer. It's the HTML, CSS, for example, managing the interface. We know that's the thing. The logic layer serves as a brain. So it's the backend server application platform like Java and everything. The bottom is just the relational or non-relational database management such as MySQL or MongoDB, etc. So this is pretty much simple. Now we know open close principle. What is open close principle? The open close principle states that software entities, classes, functions should be open for extension but closed for modification. This means you should be able to introduce completely new features or behaviors to a system without altering or rewriting or breaking any of the existing battle-tested code. Open for extension, the core principle is that the operational behavior of a module can be extended or enhanced as the business requirements evolve or change, but should be closed for modification. Extending the behavior must not require changing the original source code file, protecting the existing system from regression bugs. For example, a desktop computer. Think of a desktop motherboard closed for modification. When you want to upgrade your computer graphics performance, you do not pull out slaughtering iron, melt down the motherboard circuits, or rewire the central processing CPU. The core motherboard is closed, open for extension, meaning that because the motherboard includes PCI expansion slot, you simply plug in a new graphics card. The system is naturally open for new updates and everything, but you don't really need to just change the whole system or like modify the system itself. You just add a new graphic card to it. And that's the isolated component. Now, architectural patterns versus design patterns. We understand that architectural patterns solve big system-wide structural problems like client server, while design solve small detailed components like problems inside the code. Now, architectural patterns decision to build separate emergency wing, a central laboratory, and an isolated infectious disease ward connected by specific secure coordinators. This choice determines how patient staffs and materials flow globally through the entire facility. Now, let's look at it. Architectural patterns, macro architecture, system-wide or enterprise level. And then we have microarchitectures. These are localized inside a single module or class structure. These are design patterns. Now, focus of architectural pattern is how major subsystem database serves data and communicate. For design patterns, how individual code files, classes, interface interact efficiently. The impact of change for architectural pattern is extremely high. Changing a structural pattern requires massive system rewire, but changing a design pattern is low to medium. Refactoring a design pattern is localized and safe. The example for architecture would be client server microservices layer, the three tier, the event driven architecture. For design, the example would be strategy pattern, factory method, observer pattern. The implementation would be that architectural pattern choice are microservices. For example, the system is split into independent microserver across cloud environment. Each server communicates over web protocols. The design choice would be the strategy pattern. Inside each code, a developer needs to build an export feature so users can download their bank statement. The structure, the programmer implements the strategy design pattern locally inside the code to swap out a document formatting module dynamically at runtime based on user selection. Now we understand that if a developer decides to completely rewire the export logic to use a factory design pattern instead of strategy pattern, the localized change is completely invisible to the rest of the microservices. The global architecture remains completely unaffected at all. So what are the advantages of design patterns? So they reuse proven solutions, build quality traits directly to the system, create shared vocabulary for developers, and help you analyze old code. Meaning that reuse improving solutions, instead of guessing how dynamically swamp payment providers like Visa, MasterCard, you implement a standard pattern strategy known to handle this cleanly. Built-in quality traits are like by utilizing an abstract factory pattern to build ATM UI components, you can switch from touchscreen layout to a dark mode layout without breaking background code. So patterns are structurally uphold core object-oriented rules like open-close principle and low coupling, automatically making code easier to test and extend and improve. And we have shared team vocabulary, meaning that during a meeting, an engineer says, let's use observe pattern to notify the maintenance team when cash funds run low. The entire team instantly visualizes the complete class structure. Then there is easier legacy code analysis where you open a 10-year-old banking file and spot a class name. Because you know the proxy pattern, you instantly understand it handles access control or logging. When onboarding to a massive unfamiliar code base, recognizing standard design patterns help you instantly understand the architecture intent and data flow. Then we understand that grandmasters do not sit at chessboard, try to invent original untested moves from scratch during a high-stakes tournament. They study and deploy proven positional layouts that have worked effectively for centuries. Similarly, software engineers use design patterns to establish highly secure predictable positions in their code before tracking unique business logic. You can think of design patterns like standard chess strategies, such as defense strategy or Kuhn Gambit. These are names of different strategies that have always worked. What is a class library now? So a class library is a collection of pre-made reusable code offering general tools that your application can call upon whenever it needs them. Meaning that inversion of control. Well, no, in a library dynamic, your code is in control. Your application dictates the execution flow and decides exactly when to call the library utilities. Your program runs in regular loop and only at the very end it calls the math calculation to process a number. The scope of logic focused on generic low-level technical problems rather than business rules, string manipulation, mathematical calculation, date formatting, or basic file reading, etc. Now, the deployment would be packaged as compiled files or modules that are imported directly into your project dependency. For example, a jar.jar file in Java, or DLL in C# or package in JavaScript, whatever. So to understand class library, think of a physical mechanics toolbox. A toolbox contains pre-made screw wires or sockets. The wrench does not tell the mechanic how to repair a car, nor does it automatically turn itself. The mechanic is completely in charge of repair strategy. When they reach a step that requires turning a bolt, they reach into the toolbox, use a specific wrench or screw to perform that specific task and then put it back. Now, class library versus framework. Developer often confuse libraries with frameworks, but they operate with different opposite control mechanics. With the class library, you call it. You write the main program application and you call specific library function when you want help. Framework, it calls you. The framework acts as a massive architectural engine. It provides a pre-built skeleton structure, dictates the rules, and calls your custom code snippets at specific execution slots. Then we need to understand that what is a framework and how does it differ from library. Just like we said, that difference is that library and framework comes down to inversion of control, IOC, other words, who is running the show. When you use library, your code is in control and calls the library like a tool. When you use a framework, the framework is in control. It provides a rigid pre-built structure and calls your custom code as a specific to fill the missing business blanks. For example, control flow, you call it in class, you call it class library, and your application control the entire business logic. What does object-oriented analysis and design involve? We know that object-oriented analysis and design is a OOAD, is a structured software engineering approach that models a system as a collection of interacting modular objects. Analysis focuses on what the system needs to do by mapping real-world domain concepts. Like design focuses on how the system will do it by transforming those concepts into logical code structures, specifying object attributes, behaviors, and relationships. Analysis like OOA, understanding the domain, for example, identify the real-world objects, their data, and how they interact with users. For example, the primary question would be, what are the real-world pieces and requirements, for example? There are two different phases of OOAD. The first is analysis, OOA. You look at a physical branch, identify core entities like a customer, a bank account, and a physical cash dispenser. You note that account balance has balance. Then the second one was design, OOD. The first one was OOA, analysis, understanding the domain, identifying real-world objects, data, and how the user interacts. The OOD is building the blueprint, convert the real-world entities into software classes, define exact programmatic methods, and map communication pathways. How will these pieces interact cleanly in code? You create a UML class diagram. You define that the bank account class is a private variable and a public method, withdraw amount, for example. And this is how you try to navigate this. Now we try to ask that how you safeguard quality through architecture. Now, that being asked, we need to understand that safeguarding through we protect these quality traits by ranking and prioritizing them early in the life cycle, conducting regular structured design such as AATM, AATAM, documenting the architectural decisions and rationale, the why, to prevent future developers introducing technical depth that degrades the system, for example. Now, ranking quality needs early. Using quality attribute scenario to turn vague goals like the system must be fast into concrete metrics, like under a peak load of 5,000 requests, the ATM must process withdrawal under 500 milliseconds. This is an operational strategy. And why it safeguards quality, it forces stakeholders to explicitly choose their trade-offs. For example, prioritizing security over speed, or before a single line of code is even written. Now, running regular design reviews, conducting formal evaluations like architectural trade-off analysis method. Team sits down with blueprints before major implementation phase to actively look for risks. It then uncovers hidden architectural flaws, tight coupling, or single point of failure when they are all cheap and simple and easy to fix. Documenting the why, ADRs. So architectural decision records a brief documentation capturing the context of a structural choice, consolidated, and why is definitive reason for the choice. It prevents the historical amnesia. When a new developer joins the team 3 years later, they won't accidentally dismiss a crucial security layer because they didn't understand why it was built that way. That's why we're documenting the whys. This way, ranking needs, the engineer decides upfront, the bridge must withstand Category 5 hurricane winds, or even if that meaning using heavier, more expensive steel that takes longer to install. Then we have design reviews. That's how we safeguard quality through architecture, that we design reviews or we document the rationale. The lead engineer archive blueprints explaining exactly why they choose a flexible cable stay configuration instead of a rigid one, why they use certain technology, why use C Sharp instead of Java. 20 years later, when maintenance crew want to add extra wheel, they consult those records to ensure they don't overload the bridge structural capacity and cause a collapse.